In the last video, we looked at finding the moment of inertia of a uniform rod. In this video, we'll move on to looking at finding the moment of inertia for a rod with non-uniform mass distribution. And in the process, we'll also outline an exact approach to one-dimensional moments of inertia. So let's begin by considering a rod of length L with a density, a mass density, with value alpha x. And so what that means is at the edge of the rod labeled x equals 0, we have essentially 0 density. And our density increases as we move to the right of the rod. And in particular, we'll begin by considering finding the moment of inertia about the leftmost edge of the rod in the indicated axis. So let's outline our steps. Step one is we're going to draw a picture. Namely, we'll draw a representative dm, which I'll do right there. And then once we've indicated a representative dm, we can then draw its r, its value, its distance from the axis of rotation. Step two, we note that di, the infinitesimal moment of inertia due to that mass dm, is equal to r squared dm. And remember that our goal is to go ahead and integrate this. And so in step two, we ask, does r vary for different dm's? And in this case, yes, it does. Which leads us to step three. In order to actually rewrite this integral in a meaningful way, we need to use a density. We'll use lambda to rewrite d. So remember that lambda, by definition, is equal to mass per arc length. In this case, it's got value alpha x. In the previous video, it had value total mass over total length. So what can we do here? We can say dm is equal to alpha x dl, and therefore I is equal to integral r squared times alpha x dl. Still a fair bit to do over there. Step four, we want to introduce a coordinate system. In our last problem, this required explicit introduction. In this problem, because density is dependent on position, we were already given a coordinate system. We know where x equals 0 is. And so we want to note down a couple of things. First of all, our rod is aligned with the x-axis. Therefore, dl is equal to dx. And therefore, we also know our bounds of integration. So we can write I is equal to integral r squared alpha x dx. And moreover, it looks like we'll be integrating from 0 up to L. Step 5, what I skipped doing here is rewriting r as a function of our coordinate. In this case, we want r as a function of x. And of course, because our axis of rotation is exactly at x equals 0, r is equal to x, or at least r squared is equal to x squared. Here, r equals x. And so at this point, we're essentially done. We can say I is equal to the integral from 0 to L of alpha x cubed dx, which evaluates to alpha L to the fourth over 4. Now, so far, you may have noticed that we've always said that r is equal to x. So let's consider a scenario where that is not the case. We'll consider the exact same rod. The only thing I'll change is the axis of rotation about which we want to find our moment of inertia. And so we'll have the axis of rotation be on the opposite end of the rod. Again, step one, which is drawing the picture, is essentially done here. I've drawn a representative dm. I can now draw my representative r. And step two, we've already established that r is a function of m. And for step three, we can still say that dm is equal to alpha x dl. And so at this point, what we have written down is that I is equal to the integral r squared dm. And we can in fact also say that dl is equal to dx. So the only step we need to sort of rethink is, well, what is r's dependence on x? Well, note that at x equals 0, r is equal to L. At x equals L, r is equal to 0. In fact, in general, we can linearly relate these, and we can say that r is equal to L minus x, leaving our moment of inertia as I is equal to integral L minus x squared times alpha x dx. What are our bounds of integration? Again, we're still integrating along the entire rod. So our bounds of integration will be from 0 to L. Evaluating this will take a little bit more work, but of course it is just a polynomial integral. So we can expand. What do we get? We get L squared minus 2LX plus x squared all times alpha x dx, which again can further expand. I'll pull out the alpha out front. So we have L squared x minus 2LX squared plus x cubed dx. And now we can finish evaluating, getting alpha L squared times L squared over 2 minus 2L times L cubed over 3 plus L to the fourth over 4. So you'll notice that the units all work out, and you can simplify this to a nice number. So what have we got? We have alpha L to the fourth times 1/2 minus 2/3 plus 1/4, or alpha L to the fourth times 3/4 minus 2/3, which what does that give us? 3/4 minus 2/3. It's going to be 9/12 minus 8/12, or 1/12. So we end up with 1/12 alpha L cubed. Now, it's possible I made some careless arithmetic mistakes there, so double check me on that. Now, why do all the arithmetic? Our goal here, my goal here, was to actually compare this to the moment of inertia that we received in the original part when our axis of rotation was on the other end of the rod. Notice that our moment of inertia is substantially smaller, and this should hopefully make sense. The axis of rotation right now is on the more massive, the more dense side of the rod. And so the average distance of our mass has been reduced. Therefore, we have a lower moment of inertia.